SwayamPrabha. Digital India. Educated India.
So, welcome, second day of this lecture on high entropy alloys and their microstructure diffusion correlations. And after yesterday, we will basically continue a little bit the general introduction before we start with an introduction into the basics of diffusion. So right now, I think it's clear high entropy alloys are high entropy alloys because they are thought of being stabilized as a solid solution phase with multiple constituents because of the mixing entropy. And we have already discussed that this involves necessarily lattice distortions. And these lattice distortions, I think, are the most prominent reason for the suggestion that they could have different properties. Whether they have different properties, we shall see and discuss more close to or within the second part of this whole lecture series, because then we will go into case examples of where we analyzed different high entropy alloys based on FCC, BCC, HCP materials, going from conventional to also refractory high entropy materials. And we will also have a very short look onto compositionally complex alloys, two-phase high entropy systems. Also on their diffusion behavior, and this will be something which is very new, because I think this is the first study on interface diffusion and lattice diffusion in a material that is two-phase. And why it is the first, I will introduce also when we come to that point. I wrote here, sluggish diffusion was hypothesized to improve thermal stability. It's clear that if you have sluggish diffusion, that you will have improved thermal stability, right? Whether high entropy alloys serve to provide sluggish diffusion is something where we make a question mark, and which will be one of the important aspects of this course. This is something which we still don't really understand. Is there a cocktail effect or not? Do you have an idea of what the cocktail effect could be? It sounds like something to drink with a fancy straw in it, but if you think about metals, it's maybe a transfer. The metal transfer is not so easy. So what would you think would be an example of a cocktail effect in high entropy materials? What is meant by it is that you combine now, let's say, 5 elements into a solid solution phase, and from the properties of the given constituents, as well as the known binary alloys, you would expect a certain range of properties. But let's say for this compositional range, you would not expect, from the knowledge of the pure and the binary systems, that the alloy would be ferromagnetic. But if you now mix it, then it might turn out that because of bringing 5 constituents together, having all the lattice distortions, having associated with the lattice distortions, or really the cause of the lattice distortions, different electron configurations in the local bindings between all the constituents, that there might be a shift in the effective electronic structure such that ferromagnetism could occur. This would be a cocktail effect. So you get a new property which was not to be expected based just on the properties of the constituents of your material. There are few examples also from our own work, and ferromagnetism was observed there for the Cantor system, which we have discussed yesterday. But when we very deeply look into it, it's not so trivial, because it's not just because of mixing the constituents, but because of second phase precipitation under very specific processing conditions. And these precipitates, they are then providing ferromagnetism. They are maybe not so easily formed if you have not these 5 specific elements together. So you could call it a high entropy effect, but it's not as literature suggests, that you just mix 5 constituents and you get a new effect. There is like a secondary process, precipitate formation, forming a phase with a new structure, new crystal structure, which then shows ferromagnetism, which is involved in this. So one has to be a little bit careful about this cocktail effect, because a pure cocktail effect, as suggested initially in the paper, you throw away 5 elements and you get all of a sudden a completely new behavior. I at least have not seen so far, neither in the literature nor in my own work. Would be nice, but so far we haven't found it. Yeah, and then obviously the entropy maximization is the design strategy for high entropy systems. In the end, it's not really all of it, because then you could say you could throw as many elements together, you get higher entropy. And we just yesterday discussed, right, there is a certain confinement condition. The elements cannot be too different in terms of their electronic structure, their electronegativity, their effective radius in the alloy. Otherwise, you will not be able to form a solution, because then the enthalpic term overwhelms the entropic term in your thermodynamics. So far, as I am aware, in the metallic systems, single-phase high entropy alloys only have been found for these. And I have to say plus few phases which you would call intermediate or intermetallic phases, and they can have also been found to be multi-constituent, so you could call them high entropy intermetallic phases. Very few, but it's dominated really by FCC, BCC, HTP, these close-packed structures. And then if we go for more complex microstructures, also more serviceable microstructures, then this two-phase approach or multi-phase approach is very valid. And interstitial doping has become just recently a very strong field, because people are going for high entropy steels. You see this a lot in the literature, where the development of new steels is pushed forward. And the high entropy concept there is kind of a little bit washed out, because it's not equimolar. It's still iron will be the dominant constituent in terms of mole fraction, but it will be not as dominant as in the classical steel. So you have the other ingredients, nickel, for example, could be cobalt in it. It could also be some other transition metals. But then obviously one uses the experience coming from the normal steel making in terms of using carbon, for example, and mostly carbon, to produce alloys which have better properties, especially if one wants to go for transformation-induced plasticity or twinning-induced plasticity, trip and twip high entropy steels, and then you really need the carbon. Now, how to make these materials? You know, there is a range of methods which which probably you use yourself. And actually, they are also used for high entropy materials. There's a lot of melting synthesis pathways going on, and they use conventional arc melting and things like that. Obviously, when you come from the liquid phase and you have nucleation and then rapid crystal growth, there is always the chance to have other phases that are forming maybe in the interdendritic regions or so. So either one does post-synthesis annealing treatments and deformation annealing, this is even better. But many people go for powder metallurgy routes because they are more easy to control not only the composition but also the composition of the forming phases. Especially for very high melting material, that's also costly in terms of cost efficiency, the more prominent route. Mechanical alloying is the same basically as powder metallurgy, just going a little bit more to the extreme, right? So you basically put more kinetic energy into your powders so that you store more defects, and that means that you basically arrive normally at a structure which has more defects and has formed more grain boundaries per volume, so you get something like ultra-fine grained or nanostructured materials. They are highly unstable, obviously, so if one wants to compact them and make a bulk material out of it, then you have to anneal, probably anneal under specific conditions, spark plasma sintering, or maybe applying at least some pressure and temperature in order to make bulk shapes. But the nice thing about the high entropy systems is, as I yesterday told you, they can store a lot of defects because the dislocations cannot glide very easily because of these lattice distortions. And that means that you can still retain small grain sizes while making the material compact. And this has been shown to be working and to be efficient. Rather new addition is the additive manufacturing, which obviously has the chance to make complex geometries without losing so much material, so very cost-efficient process. And I will show you in the second part of this lecture series some results on additively manufactured Cantor alloy and specifically on the diffusion properties, because it works nicely and you get very nice materials free of macroscopic defects like cracks or voids if you do it correctly. But the grain boundary properties in this material is different from what you would normally expect. So it's has similar properties in terms of the diffusivity along the grain boundary network as materials which have been synthesized by severe plastic deformation processing. So do you guys know anything about severe plastic deformation processing? Maybe not all of you, right? So we will also introduce this in this part, but it basically means that you have a way of deforming a material while the material is in geometric confinement, so it cannot flow away. Extrusion is something which is similar to that, right? So because you extrude the material and basically you apply a large pressure and the material is in a confinement, so it cannot flow everywhere. It has to go through the extrusion channel. Similar methods exist, but severe plastic deformation means that the amount of deformation is much higher and the pressure, especially the hydrostatic component of the total strain, is much higher, going up to several gigapascals. That means you affect material in a different way because you make the vacancy migration enthalpy higher, so you limit diffusion while you process, you store a lot more defects, and this is a very efficient way to make ultra-fine-grained materials. And in these materials it has been proposed and verified by our work that their grain boundary structure is severely changed. It allows for very rapid diffusion, like 8 to 10 orders of magnitude increase. It's not just, you see a little bit more, it's really 8 to 10 orders of magnitude, which is a huge difference. And the same we find for these additively manufactured materials, which tells you that this type of processing involves very, very large strains. And if you think of it, it's basically a liquid-solid process, additive manufacturing, right? So locally you melt by an electron beam or by a laser beam your material, and then it solidifies, but you just do it in the geometrical features you like to have. Could you imagine where does the strain come from? Exactly. And this directional flow of the heat. And that basically makes shrinkage, and that makes, because of thermal expansion being different from this region to the environment, makes very huge strains, and this seems to be the cause for this change in grain boundary properties. So this is a very big effect, as I say, and so far people are not taking this into account, but it could also lead, for example, later on to crack formation in your material after additive manufacturing if you don't do anything about getting this strain relaxed out. So it's very important. And this is, I think, also leading to this point here. The challenges are achieving homogeneity and scalability. Right? So especially homogeneity is a big issue, and this is also why bulk processing in industry of high entropy materials is not yet established. I think maybe the first route where we really see this will be this guy here. So if we think of bulk, then it might be really additive manufacturing. Coatings is different, and coatings, I think, will be a much quicker way of putting high entropy materials into industrial processing. So it means that when we think of materials design in terms of high entropy systems, this is what you guys are doing probably every day, or what you at least will be doing if you are working in a job where you want to design new materials. It's really a very complex process which involves many, many different steps, right? So you have to think first of what are the properties that are critical for the performance of your final material. Then you have to select the components. You have to adjust the composition so that you are in the right range. Then probably some computational design based on Kalfat modeling will be there. But you also have to think of all these different aspects of, do you want to have a material that specifically absorbs stresses? So you want to have maybe trip or trip effects installed. Maybe you want to recycle the material, so chemical aspects come into play. Maybe the material should have ferromagnetic properties because you want to make a switch. And all of this really needs to go into your thinking and into this chain of thought in order to do materials selection and materials design. And this is the same for high entropy systems. It's just even a little bit more complex because you have to worry about a system where you don't know the phase diagram, because normally the first thing one does when one wants to design a new material is look into the phase diagrams. These are the maps for materials processing. But for 5-component systems, hardly available, right? And so there I think we cannot do anything without Kalfat. Fortunately, there is a lot of Kalfat done already, so one can look things up, but it's really important. And this is an aspect which we often don't think so much about it. So this is showing for the most used elements in high entropy systems, 3 aspects in their making. It's the energy footprint, this yellowish scale. It's the carbon footprint, meaning how much CO2 is used or is generated in the making, and also the price per kg. And you can see that there are some materials which do not perform very well. So this is something which one really needs to think about in terms of sustainability, right? And this is why many researchers try to use the high entropy approach to avoid these very kind of bad materials. So to either only stick to elements which are easily reusable and recyclable, or which do not cost a lot. And the best is to have both combined in one approach. Yeah. So this is something which, especially for the future, meaning for you young guys, you need to always be aware of, because I think everybody in this world has accepted, except maybe some politicians, that climate is changing and that we have to do something about it. And I think the material selection, even for steels, even for very normal materials which we use in our daily life, needs to take this more into account. So these are, I think, applications where one can see high entropy materials to be used in the near future. Aerospace, biomedical. Why these? It's because their performance is required and necessary. Costs per kg are not really the highest issue. If you want to make a car, costs are the three most important issues. If you want to make an aerospace vehicle, safety, performance is much more important. Energy consumption, so having lightweight, strong structures which sustain and keep their properties at high temperatures for long times, don't oxidize. You know, if it costs the double the amount of money per kg, nobody worries about it. And so this is why always in materials design and selection, if you have a new materials approach, these materials are costly, more costly initially, right? Because we don't know how to make them. We don't know really how to process them. Everything costs money. And this is why they are going to the niche applications first, where performance is required, where you can make a difference if your material is going and keeping its properties up to a temperature which is 50 degrees higher than the competitors. Then you are in the market and you sell. Then it doesn't matter how much per kg you pay. And from there we learn, and then we basically flood it into different applications. Cost goes down and applications broaden. But this is the normal way. So don't get disappointed if you make a very great new material in your PhD, and then you see, oh, nobody wants to apply it in industry. It will take time, right? Because industry is very conservative, because for them huge costs are involved in changing from one material to the other, even if you just change the composition a little bit. Because they worry always about maybe processing conditions in the big scale facilities change and so on. So be patient. Just do your best, develop good materials, and if they are good, they will be applied. But maybe not when you're a PhD, but maybe when you're a professor. So that's the normal way. And challenges are there, and I think this is also addressed mostly to you, because you are the next generation to solve them. I think this, for the research, is the most important one. How to develop really phase prediction which you can count on, and how to transfer it to something industry can use. All the other ones, I think, are more related to really application, to applied research. They are basically following what we have discussed before. And then I said future directions, developing advanced computational tools, databases, maybe machine learning is something which can be used here, because we don't really have a good system to go from binary and ternary phase diagrams to quaternary, because we don't know the multi-component intermetallic phases. We have many blind spots in these multidimensional phase diagrams. And you know, or maybe you don't know, who is doing CalFET? From you guys? Okay, nobody. So CalFET is excellent at solving large sets of equations, and also differential equations, right? So you get basically a solver, and you put in the data for mixing enthalpies, mixing entropies. That's mostly it. In some refined versions, you also put in some diffusivity data. That's called dicta, the module in Calfat. So you get also the kinetics of phase transformations as an output. However, Calfat cannot predict a new phase. Maybe that sounds strange, but that's true. So if you go to a 5-component system and you have an A, B, C2, D5, E7 compound, Calfat doesn't know about it, and it will not predict the stability, the Gibbs free energy functions for it. Right? So we have to put into the data possible phases and all possible phases. If we don't know it, we cannot put it in, and then there is a blind spot, and then we process the alloy according to Calfat predictions, but we see, oh, what comes out is not what we want because we have 1 or 2 intermetallic phases in the system that were not predicted by Calfat. And this is why experimental work is still very much valid. Or you couple Calfat to density functional theory, DFT. There, again, we put 50 atoms together, right? And then on an ab initio base, the DFT calculation can predict lattice stabilities of phases which we don't yet know about. It will just try everything, every combination, and maybe comes with this strange phase I just mentioned as a solution, maybe showing that in this compositional range, it has the lowest free enthalpy. This can be then coupled into Calfat, and then Calfat will do the right thing and will give you the right predictions. But this is just at its infancy because the DFT takes so long, and because, I mean, if you have a very complex structure, let's say, you know, some Laves phase or something like this, maybe you need to have a very large number of atoms to make the unit cell. If you don't have enough atoms in your cell to do the DFT, then the phase will never be predicted. So there is all kinds of loose ends which are fixed more and more the more further we advance, but still we are not yet there that everything can be done, you know, with the push of a button. And so this is what I mean with development of advanced computational tools for phase prediction. Then I think there is a huge open field where non-metallic and maybe composites of metallic and non-metallic hybrid high entropy materials could be of much use. I think so far nobody is really exploring this. Then obviously sustainability, also in synthesis, is a big issue. And applying these materials and their tunability by compositional tuning to advanced fields, with, like for example, quantum materials for coatings, for, let's say, chips for optical computing, where you can change the index of refraction by changing the composition. This is something which I think has really future. If you want to do further reading, I would recommend this classical book by Ye on structured high entropy alloys. Also Zenkov's work on mechanical properties of high entropy alloys. You know, this one is like the classic. And then the other one is a little bit more recent. But I would also recommend especially review articles, which you can find for example by Iso George or by Dirk Rabe. They are very good, and especially they give you a very complete set of references, which you can use then to dig deeper into the literature. I think they have 250 and more citations, so it's really done in a very good way. Any questions so far? Good. Let's shift gear and go to diffusion. If I have a block of pure gold, which I wish I would have. And it's mathematically pure gold, only gold atoms in there. Is there diffusion happening? Who thinks no? 1, 2. Who thinks yes? 1, 2, 3. Okay. Yes is correct. But the question is, which type of diffusion? Because we normally think of, and I think you also had the mental note of diffusion occurring because there is a concentration gradient, right? And so diffusion works to minimize the concentration gradient, to homogenize the material. So no concentration gradient, no diffusion. That is correct for a certain type of diffusion, chemical diffusion. But if we just have one single set of atoms, one type in a material, still we have what we call Brownian motion. So it means atoms are oscillating on their lattice position. And so maybe if we again go to our 2D representation of a crystal lattice, if we have all atoms of the same type, and I just marked this one in the middle, so I mark it, right? So it's still the same gold atom, but it's just that I know the name, the first name of this atom. Now what does it do? If for example, I apply some kBt, let T equals 0.6 times the melting temperature. Right, so there is some thermal energy in the system. What happens? Well, all these atoms vibrate. They oscillate around their equilibrium position. How often do they do this per second? So what's the typical frequency of these oscillations? It's the dBi frequency. So it's basically something like 10 to the 13 per second. So many, many oscillations per second. The higher the temperature, what happens? The larger the amplitude of these oscillations. Now, in principle, that doesn't change anything. However, if this is my atom, but neighboring to it, there is an unoccupied lattice site, a vacancy. Then it will still do this thermal vibration, but it might have, by chance, one excursion, one of these oscillations, as a statistical random oscillation, might be so large that the vacancy and the atom which I'm looking at exchange their position. So it means there is, yes, substitutional diffusion, exactly. Basically we have a diffusive jump. So if we want to have substitutional diffusion, the vacancy is close by, and then diffusive jump can occur. But it's a rare event. Why is it a rare event? You know, in my sketch, it looks like it could happen with any jump. But we have to now take into account that the lattice is closely packed. So it means in order to go from this position here, where was I? From this position here to this position here, there is an intermediate so-called transition state where basically these neighboring atoms are too close together. So the jump must be just right, or this excursion, this oscillation must have the right amplitude so that the atom can reach the next lattice position. And at the same time, because of all the other atoms also doing their oscillation, they must be just at this time of the transition be a little bit further apart so that the atom can push through. This is providing the activation barrier. This is why temperature is necessary, because if you go to too low temperature, there is no diffusion, it's frozen in. It will happen, but it will happen so rarely that we have no chance to observe it at all. And this is why I mentioned let the temperature be 0.6 of the melting temperature, because normally as a rule of thumb, at half the absolute melting temperature, measured in Kelvin, diffusion becomes measurable. Right? So if it's less than 0.5 TM, the observation time for diffusion will be much longer than any lifetime of us, so it means we don't see it. What if we have interstitial diffusion? Okay. So let's say I put carbon now into this lattice. Is there any change? Or let me ask you again a question. What do you think under the same conditions, same base material, same temperature, 0.6 melting temperature, which one would be faster, substitutional or interstitial diffusion? Interstitial, yes. Why? Yes, they occupy the octahedral site, but still, if it wants to go from, let's say, this position here to this position, it's the same thing, right? It needs to push through the atoms which separate the octahedral sites. Yeah, it is correct, but the reason is this interstitial diffusion doesn't need a vehicle, because the interstitial lattice is always there. So there is the free spaces provided by the lattice itself, and so it needs to push through. It's smaller, so that's quicker. That's reducing the activation barrier, absolutely correct. And additionally, and this is the larger part of why it's faster, is that the activation energy to create a vacancy nearby is not necessary, because you don't need a vacancy. And so it means there's two aspects why this activation enthalpy is lower, and this is why interstitial diffusion is always much faster than substitutional diffusion. So this is why we have all these problems with hydrogen in steel, because it goes through steel like a bullet through butter, right? I mean, it's really fast, and unfortunately it even embrittles the steel when it goes through. But you also cannot keep it, right? Because it's so fast and it's so quick as a diffusion process. So this shows you the small discussion that diffusion is having different aspects. It depends on whether it's interstitial diffusion, substitutional diffusion, but also whether we think of self-diffusion, gold in gold, or chemical diffusion, iron in gold, or whether we think about tracer diffusion. And this is what will be the main topic here. Tracer diffusion means we want to look at almost self-diffusion. So we have one set of atoms in our material. Now we want to make a macroscopic measurement of the diffusion process, right? And so if we just have gold atoms changing place, what do we measure? We cannot see any effect of the diffusion, so macroscopic measurements are impossible. The trick is to use now a radioisotope. So the same element, let's say gold, but having different number of neutrons in the core of each atom. We apply this tracer, gold tracer, and let it diffuse. And then we can section the material and count somehow, I will show you how, the number of radioactively marked atoms in each section depth. And this gives you a diffusion profile, and you can properly evaluate the self-diffusion coefficient, or the tracer diffusion coefficient to be correct, from these type of measurements. So this is how we will do, and this is what I will show you later on in this course, because this is the only way we can measure diffusion coefficients which are very comparable, or which are very easily interpretable as the self-diffusion coefficient. This is also what has not been done early on in the high entropy alloy work. And this is why the reports on sluggish diffusion came about, by evaluating the wrong type of diffusion measurement and then taking the values in the wrong way to interpret them as self-diffusion coefficients. And so you have to go through this. Yeah, so I will basically go a little bit to, am I in pen mode or am I? Okay. To basics, then give you a list of the literature on diffusion, on specifics of diffusion, because you can also ask yourself, in a normal conventional material, like a piece of steel, where is diffusion going? I mean, you could, let's say, apply a process gas. Let's say CO, or any type of carbon-containing gas, and you want the constituents to diffuse, let's say carbon, diffuse into the steel to carburize it. Would you expect that it goes in a very uniform way throughout the material, if it is a cast piece of steel, or is there local variations? Right. Why? What are the local variations? Where do they come from? They're coming from the microstructure, right? Because you have very complex microstructure. You have maybe several phases, or at least you have grain interiors and grain boundaries. And you have dislocations, and you have vacancy clusters. All of this affects diffusion. And the diffusivities are very different if we compare lattice diffusion, so inside of the perfect grain, and for example, short circuit diffusion along a grain boundary. Much faster, because the structure allows for more excess volume, so to speak. And so there is literature also on these specific paths of diffusion and how to describe them, based on physics, based on the mathematics of diffusion, and also how to analyze them. And grain boundary diffusion, it's like one of the things we do in my group, so I will also give you much more detailed information later on in the course. Yeah, and then we basically will also have a look at the simple Fick's laws. You guys probably know them already, but I would like still to repeat them, and specifically use that to show you the simple problems and solutions, because we will not go into the fundamentals of diffusion. That would be an independent lecture, starting really from Brownian motion, because I will just show you diffusion applied on the materials, high entropy materials, but basically like how to analyze volume and grain boundary diffusion in real materials which are polycrystalline. So basics of diffusion will give you a set of the equations which one can use and the basic, most important solutions to describe the diffusion profiles which one can measure. The radio tracer technique is important for the self-diffusion measurements. If you have understood the radio tracer method, you can easily transfer that to interdiffusion measurements, which everybody can do who has a furnace and a scanning electron microscope with EDS system, or better a WDS system. And then we will also talk about diffusion in materials which have high volume fractions of grain boundaries in their materials, so nanostructured materials, relating basically to the point grain boundary diffusion is important. Grain boundary diffusion is important also for polycrystalline materials, but it's less severe just because you have not so many grain boundaries per unit volume. But this short circuit diffusion pathway, grain boundary diffusion, is very important also for all these sustainability issues like corrosion, degradation, because they normally occur at the grain boundaries. This is, I think, important research, and even if you are not having a radio tracer lab, interdiffusion studies are very valid if one evaluates them correctly. Because you can really use them to, for example, determine equilibrium phase diagrams. You can investigate transformations, you know how to purify a material and get the kinetics out of that, optimize alloying treatments. So all of these things are specifically important for people working in metallurgy. So you really have to be aware of diffusional processes and how to use diffusion to your advantage. Because you will be using diffusion when you work in this area, whether you want it or not, because it is always involved in any transformation, in any kinetics of processing. And especially also in creep experiments, high temperature creep is governed by diffusion. And this place, IIT Madras, was formerly very well known for creep experiments. I think this was maybe the first place in the world, and I still remember seeing this huge hall with hundreds of creep machines working at the same time. I'm not sure if it still exists or not, but it was really a sight to see, I have to say. But this is 20 years ago, so yeah, maybe things have changed. But it's also important for many industrial processes. I mean, heat treatment, obviously, but also welding, also thinking of diffusion bonding, even has the term in its name. And also, if you think of microelectronics systems, right, you have to avoid poisoning of the semiconductor by the transition metal. And that's how diffusion barriers came into place. Is why we use silicon, right? Because it has this gate oxide, the silicon dioxide, which is so stable, which can be controlled and manipulated in such a nice way. And unfortunately, it's used by industry to calculate how long will your smartphone work. You know, because this is engineered to fail, because the diffusion processes will occur at the operation temperatures and a certain amount of time operating at this temperature, because then industry can exactly calculate, okay, now the diffusion process was so severe that sufficient high numbers of transition metals have entered the semiconductors, created new states in the band gap, which means the system fails. And this is, they can calculate very accurately. So this is why after a couple of years, maybe not only the warranty years, but maybe double or triple, but then it will start to show errors or will stop functioning. And this is all or mostly because of diffusive processes. Yeah, reference books on diffusion, there are many, and I think I would recommend them, especially those two which I mark here. The second one from 2007 is really a very, very complete book on diffusion fundamentals, diffusion applications, mostly really on diffusion in materials, in metallic materials, including polycrystalline materials. Excellent book. It's made for the advanced student up to the professional. So this is something which I think really covers basically all you need to know about diffusion, and it also provides you sources where to go even more into the details of the mathematical description. If you go for more specialized books, so you want to dig deeper, then all of them are good. I would say this one here by Manning is a classic, and this one here is for grain boundary diffusion, the standard book. And obviously, when you want to, for example, interpret interdiffusion measurement, you need to know the self-diffusion coefficients, and there you need to have databases, and there are good databases around for bulk diffusion or volume diffusion. And then for grain boundary diffusion, specifically this book by Gust and others. They are a little bit older, but since then there was not so much data added, so they are still the most complete ones, unless you find in the internet some machine learning tool that gives you also the newer devices. So these are diffusion processes. Left a gas, in the middle a liquid, right a solid. Obviously, we know about diffusion processes in gases, right? I mean, there is no fundamental difficulty in understanding that gases diffuse. In the liquid, we also conceptually have the same feeling, right? We know it from putting milk into our coffee or tea. There is spreading, and that's a diffusive process. In the solid, it's the same, right? And you know already, this is actually knowledge not so long with us, because only 1896, a guy actually could show that there was diffusion between lead and gold. Before, there was the saying in science that in the solid state, atoms don't move, but they move. And especially if you go to temperatures higher than half the melting temperature, then it will be visible, and we know already. What we will not do in this lecture is start from here, as I said, because we will jump ahead, and we will not go from Brownian motion to diffusion, but we will immediately start with the diffusion process. Just to give you an idea about the different magnitudes, so in gases, normally we have 10 to the minus 4, 10 to the minus 3 square meters per second diffusivities. In the liquid, it's maybe 4 orders of magnitude enhanced, and then there is a huge gap for the volume diffusion in solids, measured at the melting temperature for typical FCC and BCC metals. So if you now go to half the melting temperature, obviously these diffusivities go down a lot. Why is that? Two reasons. The vacancy concentration goes down, and thermal agitation, the amplitude of the thermal vibrations of the atoms also goes down. When you look into textbooks, where you get typically is that a diffusion length is mentioned, a typical diffusion length. This is this square root of 2 dt, and d will be the diffusion coefficient. And t is the time available for diffusion. And this is really coming from an atomistic description of Brownian motion. Because what Einstein and Smoluchowski did was evaluate the statistics of these Brownian motion. And Brownian motion would be isotropic, right? So it's just motion because of thermal energy. But that leads to diffusion, right? To intrinsic diffusion of atoms, even if there is no concentration gradient. And when we measure diffusion, we always measure, let's say, how a material as a whole moves into a certain direction. So we need to have a gradient of property, concentration, or having different number of neutrons in the core. But it's still the same thermal motion, which means that we can apply this diffusion length estimation based on the atomistic description of Brownian motion in a system not containing a concentration gradient. That was treated by Einstein and Smoluchowski. And in this equation, this is again the diffusion coefficient. This is again the time for diffusion. And this, do you know what it is? No? Did you know the term mean square displacement? That's basically the distance a particle has moved from initial position to final position based on Brownian motion after a certain time t. So it means, did you do in your early years the drunken sailor problem? Like a drunken sailor moves arbitrary, right? He wants to go from ship to find his hotel room, but he's so drunk he cannot really keep a straight line, and so he goes left, he goes right. But in the end, because of still this arbitrary motions which he does, he has reached a certain distance to where he started. And this is this mean square displacement for a particle doing Brownian motion. And so it means really the randomness of jumps is still translating into a diffusive process. And this is giving you the average diffusion length. Now, if we start describing diffusion mathematically, obviously you have heard about the Fick's law of diffusion. And the first law is just stated there. So we have here basically the diffusion equation, first Fick's equation. Relating diffusion flux to a concentration gradient. Right, so here we now have already applied the Brownian motion approach to a situation where concentrations are not uniform. So where we have a certain spatial distribution of specific atoms, giving rise to a concentration profile which is not constant. And then diffusion is the process which, because of the driving force of given by chemistry being unequally distributed, tends to smooth out the distribution of elements, meaning that in the end, after the diffusion process has completely been taken place, you will not have a concentration gradient anymore. And then the system is in equilibrium, because as long as you have concentration gradients without any other conditions, your system is not in equilibrium. Right? So it means this is a way how nature minimizes Gibbs free energy. So it means that it's really a process that's going on spontaneously. Yes. So it means that for mass transport to be described, mass transport means transport in a certain direction. We have to have a concentration gradient, at least in this form of the Fick's first equation. Is this violating what I just said when I was talking about diffusion in a system which does not have a concentration gradient? I said there was diffusion occurring, right? But I didn't. Yes, it contradicts my statement, yes. And no, because here I describe a diffusive flux. So it means it's mass transport directed. So flux always means I put in a mental plane and I calculate how many atoms net pass through that plane in one direction. And if we now look into this concentration gradient over here, let's see. Oh, well, this is the pen, okay. So let's say I have now here a concentration gradient, right? So like in this experiment where I would have carburizing gas and decarburizing gas interacting with, let's say, a steel or iron. This is my mental plane of reference. If I'm in this situation and I let nature minimize Gibbs free energy, what is going to take place is diffusive flux, which effectively moves atoms from left to right, right? Carbon atoms. So it means there is more going from left to right than going from right to left. So the diffusive process I was telling you about, where there is no concentration gradient, means equal numbers are going from left to right or right to left. Now I have an additional thermodynamic condition, meaning I have a non-equilibrium distribution of the diffusing elements, which means that the flux is unequal in different directions. It will be more in the direction here from left to right, which serves to level out the concentration gradient. And this is exactly what Fick's first diffusion equation tells you, right? So the diffusivity, this constant d in this term, is the proportionality constant giving you the kinetics of how the diffusion flux J serves to minimize the concentration gradient that's present in the system. If I wait long enough, then this will be my diffusion, my concentration profile. It will be uniform, no driving force anymore for a net flow, basically meaning there is still diffusion happening, because of atomic vibrations occurring, carbon atoms will go from right to left, from left to right, but the rates will be equal in all directions. Right? So this is, again, very important to keep in mind. Diffusion will always be there, but a diffusion flux requires a concentration gradient, if we just stick to this phenomenological explanation by Fick. We will later on in this lecture see that concentration gradient can be deceptive as a determining quantity, and we better use the gradient of the chemical potential. Does everybody know what the chemical potential is? I take this as yes. Good. Okay. Yeah. So this is the important. This is the equilibrium flux under the condition that the concentration gradient is there. But the system will not be in equilibrium if there is a concentration gradient. So the total equilibrium, meaning no, it's actually dg equals 0, right? So we find the absolute minimum of the free enthalpy. And that means concentration gradient has been taken out and been leveled off by diffusion. So this is then the total equilibrium. But the flux going from this non-equilibrium distribution of elements with a concentration gradient to the situation where basically the system is in total equilibrium is an equilibrium flux, so to speak, because you can calculate it by this diffusion equation. The concentration gradient, the green one, you mean? Mm-hmm. That is the starting configuration in this mental picture. But then after maybe, let's say, after, this is for t equals t1, and then for t2 larger than t1, it would be something like this, and then it goes down, 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 and then this is then after diffusion for sufficiently long time so that there is equilibrium in the system. Well, that's difficult to say because it depends really on the kinetic constant, which is the diffusion coefficient d. And it depends a lot on temperature because d is a strong function of temperature. And so it means if you go to higher temperature, the time will be shorter. And for different systems like combinations, like carbon is fast diffuser in iron because it's interstitial diffuser, so it will take less long, as if you think of let's say, cobalt gradient in iron, because substitutional diffusion, and it will take at the same temperature much longer to equilibrate. We also need Fick's second law to solve and analyze diffusion profiles. And basically, this is also something which I just repeat because you've had it in your earlier lectures. So what we basically use is Fick's first law plus a continuity equation, which is mass conservation. We plug them in, and then for a constant diffusion coefficient, we get this second, or Fick's second equation. I don't like to call them law because they are just equations. Important for constant diffusion coefficient. Now, if we think of the earlier example, and let's say we have a bar of material, for example, iron, and we have on the same scale here, x, spatial scale, carbon distributed along a concentration gradient, and it goes like this. Is the diffusivity constant? We can basically apply a very mental, very simple toy model, right? We have now this lattice of iron, and now we put some carbon atoms, small balls, into the octahedral sites. Once it's filled, you don't put a second carbon in, right? So it means the amount of carbon already put into some of the octahedral sites determines a lot how easy it is to find an open slot. Also, there will be some strain putting carbon into the octahedral sites, so the neighboring octahedral site probably is affected and probably is not as probable a site as if there is no one occupied around it, right? So it means going from one side to the other, making a diffusive jump, depends on how much carbon is in there. So diffusion will change the diffusivity. And this is neglected in this approach. It is almost mathematically impossible to take it into account into a form which is analytical, so you cannot write down diffusion equations if you do take it into account, because there is no solution for these partial differential equations. And this is why either you then do it numerically by atomistic simulations, or you say, okay, this is an approximate solution for the situation I am investigating, but then you have to make sure that this is really a good approximation for your situation. So always keep in mind, if you have a situation where the diffusion process itself might change the effective diffusivity, then the approach provided by Fick's first and second equation is difficult to apply, and you have to be very careful analyzing the situation whether you are doing it correctly or not. Yeah, I mean, if the diffusivity is not constant, then you will arrive at a different equation here. So this equation, which I'm highlighting now, this one here, will not have the same shape. It will not be such a simple differential equation. It will have much more terms, because then you need to take into account a time and spatial dependence of the diffusivity itself, so you cannot easily linearize it. Yes, always the jump, yeah, I mean, this is also an assumption, because you're absolutely right, I didn't say that, thank you for the comment. If you have a specific site, your interstitial atom is here, let's say, maybe I just put it in a sketch. So again, let's say I have my 2D lattice, and I have an interstitial here. There is a probability for going here. There is also a probability for going here. And there is a probability for going here. And for all other sites. But the probability P1 is much, much larger than P2, 3, and so on. Right? So these are the probabilities. So it means this is also part of the general assumptions for deriving these equations, that we look only in nearest neighbor jumps as the most probable ones. And this gives them these equations. And this is why these correlation factors come into play, because they basically just tell you how many next neighbor sites are there. This will depend on the crystallography of the lattice, period. And then if we have this mathematical framework of first and second Fick's equation, then basically we have two important solutions, so basically mathematical solutions to the diffusion equation that depend on the boundary conditions. As you know, partial differential equations need a boundary condition to solve them. And these boundary conditions which we apply are basically describing the experimental setups one uses for doing diffusion experiments. One is called the thin film or instantaneous solution. It's a Gaussian solution, and it means that you basically have a geometry like here. So this is like the idealized geometry. So you have marked atoms B, which are forming a source for diffusion in between two semi-infinite half volumes. So it means in reality you have very large chunks of material A put together, but in between there is a very thin layer of whatever diffuses. Could be in impurity diffusion, so B is a different atom than A. It could also be self-diffusion, or better to say tracer diffusion, where B would be an isotope of A. What do? You then prepare just the pieces, you bring them together so that you don't have any oxide film or anything in between, so that B and A have good contact, and then you basically anneal it, right? So you apply temperature and time. Temperature, again, you go probably to temperatures around or above half the melting temperature of A, so that diffusion becomes measurable. You wait for a certain time t, and for experiment, we never know before you do the first test experiments what is a good time to wait. This is the experimental finding. And then you get this distribution, which is indicated by the slightly more dark bluish color being, washed out to the ends. So B was diffusing into A to both sides because the situation is symmetric, and probably the time was not enough so that B atoms reach the far ends, which also is important for the boundary conditions of this type of solution, because the infinite half volumes A should be so large that within the experimental time t at temperature capital T, the end should not be reached. And then, since B is only available as a thin film, it means it's a finite amount of atoms. So it means it's not that the composition stays constant in the middle between these two A blocks, but basically it's so few atoms of B that all of them diffuse, and the composition varies everywhere in the final volume A1 plus A2 plus original B. If these boundary conditions are taken into account, then the diffusion equation has this solution. That's called the Gaussian. Solution. That's the in most cases in research we apply this type of diffusion measurement. We have a constant, very thin source for the diffuser, which basically is not constant in composition, but which basically is so few that it goes down in concentration, and then we get these very nice diffusion profiles. And then we basically can describe the composition profile by this equation, and what one really wants to get is this guy, right? Because we know the time and everything else. There is a second way of measuring, which is the thick film or constant solution. And that means, for example, also if you are having a diffusion process inside of an environment, let's say a carburization, a nitridation treatment, then you supply normally the gas which comes into your reaction chamber, and it is also going out. And some of the gas is basically by diffusion changing the structure of your material. So it means that the diffusing species is constantly replaced by your external volume, which you feed into the system. So it means, unlike the previous solution, the composition of the diffusing species stays constant. It's the same as if you would apply a very thick film of marked atoms onto a material. Now you let it diffuse at a certain temperature, capital T, for time t. but there is so much of it that still at the end of your diffusion process, the composition of this diffusing species at the place where you applied it is the same. This is then what's called the thick film or constant solution. Constant because the composition of the diffusing species at the place where it was applied will stay constant. Then the boundary conditions obviously are different for solving the partial differential equation, giving rise to the error function solution, which is indicated here. And you can see, again, we know the time and all other things, so we can get the diffusivity out of it. But the concentration profile looks really different, right? And so it means if you do diffusion experiments, and if you now apply a certain amount of material on your matrix, on the material where you want to measure diffusion coefficient in, you need to know, did you apply a thin film? And will the concentration vary? Will it be consumed during the diffusion process? Or is it a thick film and you will have a constant source solution? Because in the way you will then separate the material, we will count how much atoms have diffused up to which depth. This gives you a diffusion profile, but the way how you fit the diffusion profile to obtain the diffusivity D will depend on your boundary conditions in the experiment. If you don't know them, maybe you evaluate it in the wrong way. So if you apply an error function solution to a situation where a Gaussian solution would be appropriate, you get the wrong D. So it means that you really have to test and think about how to set up and plan the experiment so that you know how to evaluate the data in the end. So maybe now getting to reasons for diffusion, different types of driving forces. As I said, diffusion is different, is occurring because of concentration. Diffusion is always happening. Directed diffusion giving rise to a diffusive flux is occurring when you have a concentration gradient. But in the end, and I will show you this in a minute or maybe next time, is when you have actually a gradient of the chemical potential. And next thing what I will discuss is that we have situations where the concentration gradient as a describing function will give us actually a wrong result. It will give us a result of diffusion happening in 180 degrees different direction as it occurs. So it's actually something where in a written test you would get 0 points for the answer because it's actually opposite to what is observed. Let's maybe get through this a little quick. I guess you know all of this. So we have a situation where we have basically, we bring two materials, two blocks together who have a different composition. So they have different amount of A atoms and B atoms in their volume. And this corresponds, if we look at this curve here, to kind of two different positions in this Gibbs free energy curve, P and Q. So now we have to remind us of basic thermodynamics. Now we have connected the two blocks, which means they now can be described by a joint common energy functional. So the Gibbs free energy is now that of the whole system, not of the two separate systems as before, right? So initially when we join, how large is the Gibbs free energy of that system? So how do I construct it? straight line between these points, right? Yeah. And so if the proportions are correct, this would be the free enthalpy of my system, right? How would it develop over time? It wants to go deeper, right? It wants to reach the bottom. So it means it goes here. This is what nature does, right? Energy minimization. Now, here, when we consider this, we see that this solid curve is a continuous curve, right? So it means this is something like a complete solid solution phase going from A to B. And obviously what I just described by Fick's law, going down the concentration gradient, is actually happening here, right? So we go from positions which are higher in concentration to positions which are lower in concentration. Incidentally, not incidentally, but it looks like it, we can also describe here this situation by using chemical potentials. And the chemical potentials are just the tangents to the free enthalpy curves, dg by dx or dc. And that means it's shown here, right? So these dashed lines are the chemical potentials for the given situation. And basically what we can describe then is a diffusive flux also being driven by the gradient in the chemical potential. In this case, the chemical potential gradient and the concentration gradient is pointing in the same direction. So it means we get basically the same description. So Fick's law is confirmed also when we use the chemical potential gradient as the driving force for diffusion. So that's fine. Now we go to a different system. We have now a phase diagram where we have a positive enthalpy of mixing, giving rise to a miscibility gap in the solid state. And so our system is really important to be looked at this temperature here. So we do the same mental thought experiment, right? So we have a block P, a block Q, we bring them together, have one unified system, one energy functional to describe the whole system. So what happens? What happens is shown here. This is again free energy as a function of composition, and these are our starting states. Wow. What happens now? They will go in this direction, right? Yeah? Do you like this scenario when you think of Fick's equation? Not really, no good, ne? What's happening is uphill diffusion, right? So the more concentrated part of your system is getting more concentrated, and the less concentrated one is less concentrated. So A atoms in the A lean material even move out to the A rich part, and vice versa. So that's really something which you would not get from Fick's equation if you plug in the description based on the concentration gradient, because here the diffusion does not serve to make the concentration gradient smaller so that in the end you get a uniform distribution. Here it makes it steeper. But if we now again apply the description based on chemical potential gradient, then it comes out correctly. So that means that the diffusion serves to make the gradient of the chemical potential less steep. So it means the description based on chemical potential gradient always describes it in a correct way so that the diffusive flux coming out of the equation is correctly described in the correct direction. If you use concentration gradient, you have to make sure you understand your system very well, because there might be a minus necessary to account for uphill diffusion going the wrong direction according to how the concentration gradient is present in your material. Does this make sense, or do you have questions? Okay, good. So potential gradient, chemical potential gradient is the important point, and it's always the correct description, whether it is uphill or not uphill diffusion. So now let's talk about, maybe not today, but just as an introduction for next time, how to now set up an experiment to try to test intrinsic diffusion of the elements which are part of the system itself. So you don't apply a new element to the system, because that will basically have different interatomic interactions, right? So you never know, is this changing the structure locally? Is the diffusivity of that really describing the atomic mobilities in your system correctly or not? So we need to have a certain methodology in order to measure how atoms which are part of the system you are investigating move, motion, diffuse through the lattice or the defects of your system. And that is radio tracer diffusion. So one needs to have radioactive isotopes. Why radioactive isotopes? Well, because you basically have the same chemical nature, the same electronic structure of your material. The valence electron concentration is the same, so a different isotope still has the same electronic structure. It just has a different number of neutrons in the core of the atoms. Is this giving rise to a concentration gradient? So am I allowed to use Fick's equation? These are the nice questions if one has an oral exam. It definitely is, right? Because you have a different species. It has more weight or less weight, depending on whether it's more or less neutrons in the core. Difference can be only up to 2. But still, the interaction between this isotope atom and the non-isotope atoms surrounding them could be slightly different because of the different masses. So like the atomic vibrations would maybe be a little bit different at the same temperature of this isotope as compared to the surrounding atoms. So it gives rise to, at least formally, being allowed to describe this as a different concentration gradient. So we can apply Fick's law, chemical potential difference. There will be a small gain in mixing entropy also by adding isotopes into a material. So it means all the thermodynamics we are allowed to use in the normal way, as if it would be a different species of atom. But the difference is very, very small. And so we are allowed to approximate this as if we would have just, let's say, an atom of different color, but otherwise equal properties. And so we describe diffusion of like atoms, but still describe them in the framework of Fick's diffusion equations as if there would be a concentration gradient. Right? So it's kind of balancing on a very thin wire. We have differences enough to be able to use this framework of equations, but they are not so large so that it would disturb the system as a foreign atom would do. And this is the beauty of tracer diffusion, that you can really work on this thin wire, even experimentally, to get diffusivities of your system. Now I think it's about time to conclude. Is there any question? Remark? We would need to draw this diagram, but as a triangular prism, because we would have A, B, C, and we would have free energy going up. And then the different pairwise interaction enthalpies would serve to generate what we would call the energy landscape. It's a fancy word for just meaning you map out the potential energy or free energy as a function of composition. And this would be a 2D curve over a 3D body. And depending on the pairwise interaction enthalpies, you would have different curvatures, or you could have different curvatures. You know, between A, B, it could be like this, so it's convex, but there could also be a concave part to element C. And this would give rise to uphill or downhill diffusion depending on where in this triangular energy landscape you are. So it could be very, very complex. Bond length is maybe a good descriptor, but it's not always true. I mean, basically it depends on, I would say, mixing enthalpy, and mixing enthalpy is a good effective value to describe all the interaction parameters based on valence electron concentration, electronegativity difference, and bond length difference. So it's all crammed together in a very complex way we don't quite understand very well. We have to do electron structure calculations for each binding in order to find out. So quantum mechanics is necessary in order to get a full picture. But the good thing is, for the thermodynamics, which work pretty well, we just need the coarse-grained description based on mixing enthalpies. They are a very amazingly accurate description of the interatomic interactions, even we don't understand, or we cannot mathematically go from mixing enthalpy to quantum mechanical interaction. This nobody has done so far. But we know we can use the easily available or more easily available mixing enthalpy terms in order to describe our system, derive all the processing and mixing terms and so on. But if you want to have a description based really on the interatomic interactions, you need to do quantum mechanics, and full quantum mechanics calculations you can do for maybe 2 or 3 or 4 atoms at the most. So not even 50 is possible. So maybe when I'm in retirement and you guys rule, you can do it, but so far nobody has done it. Thank you for the question. Any other question? Okay, great. Then I think we see each other tomorrow. Then this day 2 is over. Maybe just an announcement for the procedure. Professor Shankaran, who's sitting in the back, and me discussed yesterday that we will basically keep the schedule like 2 lectures each day, starting at 10 every day. And we will not do the 3rd lecture on some days, but we will collect all the 3rd lectures into 2 more days in the end. So we will have, our original schedule was based on 10 days, and now we will have 12 days, but every day 2 lectures. I think this is better because maybe going for the 3rd lecture in a row is a little bit straining for everybody. So maybe it's better to keep it to 2 and then reconvene at the next day. All right, thanks a lot. See you tomorrow.